It seems to me that we are all good, and
Okay.
we can start now, Professor.
Very good.
So I will welcome everyone. Thank you very much for being here in this new geotechnical seminar at University of Chile. And today we are very happy and very honored for the opportunity to learn a lot about an iconic building and how that impact the design of foundations. And for that topic, we are today with Professor Harry Poulos, who is here with us from Sydney. Hello, Dr. Poulos. How are you? How is everything back there in Sydney?
We're doing okay. All good here. Thank you very much.
How is the weather down there in Sydney today?
It's raining and cool, but it's early spring, and this is quite normal.
I see. You are in the future. What time is already in Sydney?
So yes, it's tomorrow for you here. It's
tomorrow
8 o'clock in the morning, Thursday, 22nd.
I see. Okay. Well, thank you very much for being here with us, for sharing your knowledge, your expertise. We are very happy for the possibility to learn from you, especially about this awesome topic. Here in Chile, we have a very tall building, and the heights are increasing every year. Just before starting the lecture, I wonder if we can make you 3 questions.
Sure.
The first question would be, how is it that Professor Poulos became Professor Poulos? How was your academic career? When did you realize you wanted to be a geotechnical engineer, that you wanted to be a professor, and how it happened that you became related to projects of such magnitude like the Burj Khalifa?
Okay. Look, I think I first became interested in geotechnical engineering as an undergraduate student, and I was influenced by the textbook by Terzaghi on theoretical soil mechanics. It was a book that I didn't fully understand, but it seemed to me to be really an interesting area, and I had 2 main areas of interest: structures and soil mechanics. And I found soil mechanics to be more interesting in that every problem seemed to be a different one, whereas in structures there was a lot of repetition. And so when I graduated, I decided to go on and do a PhD under the supervision of Professor Davis, who was my soil mechanics professor. And I got a PhD, and I worked for a year with a consulting firm doing structural design, actually. And then a position at the University of Sydney came up, and I applied and got it. And my academic career then followed over the next 30 years or so. And so I guess I was lucky enough to advance to the position of professor in 1982. And I stayed at the university a total of 36 years, but before that I actually moved to a consulting firm as well. So I had 2 jobs for 12 years, one as a professor and the other one as a consultant with a geotechnical company. So
very intense.
Yeah, well, but it was a good time because I was able to take real problems from consulting back to my PhD students at the university. And so we did a lot of interesting research, applied research at that stage.
Very nice. Very, very nice. And so your entire career was affiliated with University of Sydney?
Yes, certainly the early part of my career. I was an undergraduate, then a postgraduate, then an academic member. And
nice.
And I'm still an emeritus professor at Sydney University. So I guess I won't even tell you how many years that is, but it's more than much more than your lifetime, I can tell you.
So you are strongly attached to University of Sydney.
Yes, although these days I don't do any teaching, but I'm still associated with the university, yes.
Very nice, very nice. And well, this leads me to the second question. Do you have any current projects of related to research, or you are focusing mostly on consulting these days? And which has been your favorite projects? A lot of little questions in one.
Yes, okay. Look, I do have some current projects. They're not quite recently, and I'll talk about one of these more recent ones in my lecture, but there's a picture of it on the screen, the Dubai Creek Tower, which, if it's ever completed, will be the tallest structure in the world. Significantly taller than the Burj Khalifa. And I helped the company Oricon. I consulted for them in the design of that foundation. At the moment, I guess I'm doing more local projects here in Sydney. There's a big redevelopment of the fish markets here, and so I'm advising the contractors on that particular project. And I've been involved with some road projects and bridge projects as well. So yeah, I am sort of tending towards retirement, but I still can't retire because life's too interesting to retire.
Exactly. You're having a lot of fun.
I'm having fun, yes. And my view is, while I'm having fun, I might as well keep on doing what I'm doing while I'm able. You ask about my favorite projects, and obviously, I guess the Burj Khalifa, because it was at the time and still is the tallest building in the world, and it had a lot of challenges, which I'll discuss in a little while. The other project that remains in my mind is a road project I was involved with in Greece, the Egnatia-Odos project, which is more than 700 kilometers long, going from the west coast of Greece to the eastern border with Turkey. And I was on a specialist panel with three very distinguished gentlemen, Professor Everett Hook from Canada, the late Professor Paul Marinos from Greece, and Professor Heinz Brandl from Austria. And so we were a sort of expert panel of four advising on problems related to well, I was involved in slope stability and stabilization problems there. So
what a panel.
It was a great project. And of course, it was an opportunity to visit Greece a number of times over a period of 4 or 5 years. So it was a really good project.
You are a Greek descendant, as much as I understand.
That's correct. My parents migrated to Australia before the Second World War, and I was born here in Australia.
I see. Very nice. And Professor, with so much geotech, do you like what do you like to do in your free time? Do you have any hobby that not everyone knows about Dr. Poulos, for instance?
Well, in my younger days, I played quite a lot of sport, in particular cricket, I guess, and golf. But with the passing of time, that's now behind me. But I'm a big reader. I do a lot of reading, and I collect books. And I'm also at the moment doing a family history project. So I'm trying to go back and trace some of the history of my family. And so that's nice. Something that is entertaining. And I guess it also reflects my interest and love of history as well, because I think
okay. Do you like history a lot too?
Absolutely, yes, yes.
I see. Well, your how you call it, the country of your parents, Greece, is full of history.
It is indeed, yes.
Full of history and full of geotech also. There is a lot of geotech.
Yes, there's a lot of problems in Greece, geotechnical and other problems, of course. But no, it's a good place, and there are some very, very capable geotechnical engineers in Greece.
Absolutely. Greece is a wonderful place indeed. It's a wonderful place indeed. So, well, thank you very much for sharing all that part of your life, Professor. We really appreciate it. Well, we are very happy, very excited about your presentation, your knowledge, and all the little details that you will share with us about these great projects that you are leading. So thank you very much again. I will turn off my mic and my camera so you can start your presentation. Thank you again, Professor Poulos. Thank you.
Okay. Gracias, Felipe, and buenas noches, damas y caballeros. Now you've heard the extent of my Spanish, and thank you very much for inviting me to give this lecture. What I want to do in the next 45 minutes or so is to give you some of my views on the design of foundations for tall buildings, some of the problems that can arise with those foundations, and some of the solutions that can be used. And the outline then is that I'll talk about the design process that we've developed. I'll talk about some of the risks associated with tall building foundations, some of the problems that we can encounter and how we can solve them. And then I'll talk fairly briefly about 3 examples, the Burj Khalifa, the Dubai Creek Tower, both of these in Dubai, and then the Millennium Tower in San Francisco. Now, the number of tall buildings, this graph is from the Council for Tall Buildings and Urban Habitat. And what it shows on the vertical axis is the number of tall buildings that have been completed, and on the horizontal axis are the years. And you'll see there's been an almost consistent increase in the number of tall buildings. These are buildings, I guess, in excess of 300 meters. So these would be super tall buildings. And there was a slight dip in 2019, but I think the number of buildings continues to increase significantly. And some of the aspects that are in relation to tall buildings are that we have high vertical loads, and they tend to increase non-linearly with height, because the taller the building, the more robust and heavy it has to be. We normally also have low-rise areas, podium areas as they're called, adjacent to the tall tower. And so we have the potential for differential settlement between the tower and the low-rise area. We have high lateral forces and moments. Those forces and moments are cyclic in nature. And we also have to design for seismic forces due to earthquakes, which give rise to 2 types of forces: inertial forces, as we call them in English, which are forces that are caused by the building moving backwards and forwards. And the second source is what we call kinematic forces, which are induced in the foundation system because the ground is moving backwards and forwards and impacting on the foundation system. And then also we have to make sure that we design for human comfort. So we have to design the dynamic response of the structure foundation system so that you don't have excessive movement and vibration. Now, here are some of the interesting aspects that make tall buildings different. In particular, in recent times, there's been a tendency for taller towers to be located on smaller footprints. And we have now a number of buildings, and I've shown a couple of these here, where the aspect ratio, that is the ratio of the height to the width of the building, is in excess of 20. And that's normally we would be 8 to 10, perhaps, as a ratio. So this has given rise to big issues with respect to lateral and overturning stability of the foundation system. So the consequences of these sorts of differences between tall buildings and other foundations are that even uneven settlements can be very visible, that the consequences of failure can be catastrophic. And so for these reasons and others, we need to have detailed ground investigations. Usually there are a large number of piles or barrettes involved. Load testing really needs to be done, and fortunately now is becoming quite common with major projects, and peer review is now much more common than it used to be. Now, some of the ingredients for economic foundations are firstly that we have to have the right concept for the structure and the ground conditions. We have to have the right design criteria and the methods of design. We have to have appropriate ground data and design parameters. We need quality construction, of course. We need to do appropriate pile testing or foundation element testing. And ideally, we need to also monitor the performance of the building during and after construction so that we can satisfy ourselves that what has been constructed is in accordance with our design intent. Just very quickly and simply, we normally have three types of foundations that are used for tall buildings: the raft foundation or mat foundation, which is suitable for buildings on good quality rock and perhaps that are not too tall. Most of the tall buildings are on some form of pile foundation, either fully piled, where the piles are designed to take all the load, or in more recent decades, the piled raft foundation, where it's recognized that the raft or basement slab can provide stiffness and resistance to the foundation system. And so that can enable us to reduce the number of piles and also to assist in the sustainability of the foundation system. So the foundation design criteria, the things that we have to check for: ultimate capacity, of course, of the foundation system, the settlement and differential settlement and the tilt of the building, the response to lateral loads and moments, the dynamic behavior and the earthquake response. And then, of course, these are geotechnical issues, but we must also be aware that the foundation system has to be designed for adequate structural strength and also for durability. And these days, it's not uncommon for specifications to require that the foundation system will be durable for at least 100 years. Now, in the design process that we adopt, we have three stages that we normally consider. The preliminary stage, which is the earliest stage where we develop the foundation concept and decide what is the optimum type of foundation, what's the best piled raft or a pile. Then we go into a detailed stage where we develop and optimize the design. And importantly, we interact closely with structural engineers. And then in the final stage, we do the final design, hopefully with the aid of load test data so that we can optimize and finalize our designs. And here also we incorporate peer review considerations into that final stage. And I've got a note at the end that design tools that we use should be consistent with the stage of design. In other words, it's not sensible in the preliminary stage to start off the process using three-dimensional finite elements, because normally we don't really have enough detail of what our final foundation concept will be, nor do we generally have all the geotechnical data that you would require for a detailed analysis. That normally comes in the final stage. So the analyses that we do then include ultimate limit state analyses, where we examine the overall stability and geotechnical capacity. We also normally allow for cyclic loading analyses because we recognize that if there is an adequate or a large amount of cyclic loading, there is a potential for the reduction of skin friction of the piles. And what we try and do is to design the piles so that the cyclic loading will be no more than about 50% of the shaft friction capacity. In terms of serviceability or allowable movements in settlements, typically we specify no more than 100 millimeters, although some buildings in Frankfurt in Germany have settled 150 millimeters or so without any damage. And we try and limit the differential settlement or angular rotation to 1 in 500. We have dynamic loading where there are requirements for human comfort. So you have vibration and frequency requirements. And as I mentioned before, we also need to make sure that with earthquake loading, we take account of both the inertial loads due to the structure and kinematic loads through soil movements. The geotechnical parameters, the main ones that we need to assess in our foundation design are, of course, the ultimate shaft friction and end bearing. And if we've got a pile draft, we also need to know the ultimate bearing capacity of the raft. We need to estimate the soil stiffness or the modulus for vertical loading, bearing in mind that for long-term dead and live loading, the modulus is generally smaller than it is for short-term loading, such as wind or seismic loading. And it's important that we distinguish between those two when we're looking at long-term settlements and at short-term movements due to wind loading. We need to estimate the ultimate lateral pressure so that we can design the piles for lateral loading. We also need to have soil stiffness or modulus values for lateral loading because they will generally be different from those for vertical loading. And we also need to estimate dynamic soil stiffness and damping of the soil in which the foundation is located. There are a number of soil structure interaction issues. When we do our stability calculations, we of course need to check with the, firstly, that the geotechnical resistance is adequate. And what we do here is that we factor down our estimated geotechnical capacity so that we make sure that the factored down geotechnical capacity exceeds or equals the factored up loadings. But we don't factor down our geotechnical resistances when we check for the structural loads in the foundation system, because that would artificially limit the amount of load that the piles can take. We need to be aware that the stiffness of the superstructure will affect the settlement and differential settlement. And this is best taken into account in the structural analysis using values of the stiffness of the piles and the raft, which we provide to the structural engineer. And I've just got a note here that some of the software that is available commercially assumes that you have a rigid raft. And that isn't always a good assumption for tall buildings, particularly buildings that are 50 or 60 meters in extent, because even fairly thick rafts, as I'll show you later, can be relatively flexible over those sorts of distances. And it's important then that we have cooperation between structural and geotechnical designers. That is essential for a successful outcome. And one of the key geotechnical outputs that we as geotechnical designers provide to the structural engineer are values of the pile stiffness, the axial, lateral, and rotational stiffness for each pile within the group. And these stiffness values must take into account the fact that you have interaction between the piles in the group, and that affects the stiffness of the piles as compared with a single isolated pile. Those values that we provide to our structural designers are then incorporated into their analysis to obtain structural design actions or loads And that takes into account also then the effects of superstructure stiffness and allows us to get a more accurate assessment of settlements, differential settlements. So that's the design process. Now, in reality, we have a number of risk factors in foundation design. It's possible, and has unfortunately been the case in many past projects, that we do inadequate investigation, and so we finish up with an inappropriate ground model. We also may have to contend with the reality that geology provides what I call imperfections. These are non-ideal conditions. For example, we may have a softer layer below the tips of the piles. We may have sloping bedrock or uneven thickness of layers. We may have boulders. And then in terms of the construction process itself, there may be problems or imperfections or deficiencies in that construction process. So just very briefly to illustrate some of these risk factors, here's a hypothetical situation where we put down 2 boreholes and we think that those boreholes show that there is a horizontal soil layer with a stiff stratum underneath. But what we miss here are 2 important factors. One is that there may have been an old riverbed in between, and so we miss that out. And if our boreholes don't go deep enough, we miss the fact that there is a compressible stratum below that stiff stratum. So that can lead to a very simplified and incorrect ground profile, which can in turn lead to problems with our foundation. And we'll talk about that towards the end of the lecture. And here are some of the geological imperfections. This first one shows a case where there are compressible clay seams in the rock into which the piles are founded. This diagram, top right, shows strata of varying thickness or sloping bedrock. And what happens there is that because the piles are of unequal length, there is a tendency for the foundation to rotate a little. The next one, bottom left, shows a situation where you have compressible stratum under the founding stratum. And that may not be detected when you do pile load tests, because with a single pile, that compressible stratum may not influence the results very much. But for a wide pile group, that compressible stratum can be very influential. And finally, I've got in this particular case, situation where you may have boulders in the ground. This would be particularly where you've got glacial deposits, and you may install a pile which you think is on rock, but that may be just a boulder, so that the pile itself is not really on rock, but is on a boulder which acts like an enlarged base. And of course, we can have imperfect construction. Here are some unfortunate examples of board piles, which are very imperfect, as you can see. And here are piles that are not very attractive because they're not what we assume in design, which is in design, we assume that the piles are perfectly homogeneous vertical cylinders. And in reality, that is certainly not the case here. So what are the consequences of those imperfections? Well, in terms of the design issues, we need, if we've got a situation where we have uneven settlements, we need to try and correct the settlements to reduce the differential settlements. And we have 2 classes of methods, hard and soft methods. I'll describe those in a minute. We then need to design remedial or enhancement works so that we increase the resistance of the foundation system. And we need to be aware of the load sharing between old and new elements. Now, I mentioned methods of correcting uneven settlements. Here we have some of the hard methods. These are methods where we actually do put force on the foundation system or the building to try and correct the uneven settlement. We can use anchor stressing or additional loading on the high side to try and get the high side to settle more. We can try cutting the piles, but that generally isn't that effective, and it's a bit of a terrible process. We can try jetting the soil below the pile tips. We can try jacking the foundation on the low side to jack it up, but that isn't always effective, because as you jack up, you also, because of Newton's law, have a force that goes down, so that may not be effective. And also, one of the other methods that has been used is fracture grouting to try and jack up the low side, but that is also not a very controlled process. We have then what I call the soft methods, which basically involve doing something to the soil rather than to the structure. So we have the possibility of doing soil extraction. So we remove some of the soil from the high side to try and induce extra settlement and so reduce the differential settlement. We can, in principle, try dewatering, although that's not always a good idea. We can try compensation grouting so that we lift the soil on the low side, and we can then also try what I call removal of soil support. Just by way of illustration, these two diagrams show where soil extraction has been used in two cases at least, and there's been many more. Here in Iran, there was a grain elevator terminal that had settled unevenly. And so what was done here was that they constructed a trench and then put in horizontal saws to try and remove soil from the high side increasingly. And so they did a series of saw cuts of the soil to remove it and induce the high side to settle more, and so reduce the uneven settlement. And then this one on the right-hand side, the very famous Pisa Tower process, where a series of inclined boreholes, auger holes, was introduced under the high side of the tower, and soil was augered out. I think there were 43 boreholes in all, and that corrected the lean of the tower by about half a degree. And Professor Berlin, who's involved in that project, has estimated that that will increase the life of the building by some 300 years. And I mentioned the removal of soil support approach. This is a method that has been used in China, and we almost used it in Hong Kong for a tall building, but it involves drilling a series of boreholes outside the footprint with the idea of trying to remove the soil support and therefore cause some additional settlement on the high side of the building to reduce the tilt of the building. In terms of enhancement works, we can try to repair the existing piles, but that if you've got defective piles, but that can be difficult. Normally, what we try and do is to extend the pile caps to strengthen and stiffen the foundation, and then add new piles as well to try and get a better, a more solid foundation system. We have to be, however, very careful that when we do remedial work, that we don't make the problem worse, because what happens is that when you're installing piles, you cause ground movements inevitably, and those ground movements can affect the existing foundation system. And that will also happen if you do excavation for the pile cap itself. And in both cases, what you're doing is that you're disturbing the ground under the high-rise building, which is now highly stressed. And so the effects, the ground movements due to your construction operations are much more severe than they would be in what we call a green field or a level site with no building. What are the measures that we can take to reduce risks? Well, I think certainly the first thing we can do is to have an independent peer review of the ground investigation report, and then an independent peer review of the foundation design. independent supervision of foundation construction to try and avoid the problems of construction imperfections. We need to be able to do foundation testing of the piles or barrettes. We need to monitor the settlements during construction and compare what we measure with what we predict. Because if there is a problem, the sooner we can detect it, the sooner we can start to fix it. And we should treat these measures, they all involve money, of course, but we should treat them as investments in insurance rather than as costs. Because in the end, if you don't take these measures, the possible cost of fixing the problem can be very great. So let me talk about the three case histories now that I have had some involvement with. The Burj Dubai, as it was originally called, or the Burj Khalifa in Dubai. These are the original architect's concepts, the drawings for them, and it was to be and is still the tallest building in the world. These are the challenges then, the world's tallest building. We had ground conditions which involved carbonate soils and rocks, and we were aware from other projects that the foundation capacity for piles and these type of ground conditions were not as good as for normal silica-based materials. There were also concerns about the effects of cyclic loading on piles in this type of ground because we'd had experience from offshore projects where cyclic loading had caused a severe reduction in capacity of the piles. And of course, we had the ever-present problem of controlling the differential settlements between the high-rise and low-rise areas. So here is a photograph of the site of the Burj Khalifa as it was when ground conditions started. I should explain that I and my company, Coffee, were the geotechnical peer reviewers for the main designers who were Haida from the UK. And in this diagram on the right-hand side, I don't know whether you can see my cursor, but there are two buildings. These are the Emirates Twin Towers, which we did the foundation design for and for which measurements were taken. And so we learned quite a lot from that project that we then brought onto the Burj Khalifa project. The site characterization was fairly significant. There were 30 boreholes. There were SPTs done on the upper strata. There were pressure meter tests done in 5 boreholes. There were a lot of piezometers put in there. And importantly, there was geophysics done using cross-hole tomography. And the geophysics there had two purposes. One was to give us profiles of the shear wave velocity with depth so that we could get other estimates of the stiffness of the ground. And also it was a way of estimating and assessing the uniformity of ground conditions, because obviously 30 boreholes, even though there's quite a lot of boreholes, there could be possibly geological features that we miss, and geophysics can identify those sorts of geological problems if they exist. Fortunately, in this particular case, the ground conditions were very uniform, and this is a simplified profile. We had some silty sand up near the surface, and then a series of layers of cemented calcareous sands and rocks, so that they were actually essentially soft rocks with typical unconfined compressive strengths varying from maybe 1 to 3 megapascals. And this shows the base of the tower, the raft of the tower, and the base of the piles. So in fact, the piles were not very long. They turned out to be 47.5 meters long. And if you draw this in scale, the building itself is 828 meters. So you'll see that the foundation is about 5% the height of the building. The initial pile design, and I should say that we and Haida worked very much in parallel rather than in series. We worked very closely at all stages. We were involved in the ground investigations, in assessing the ground model, and in doing the design. And so it wasn't a process where Haida did their design and then they passed it on to us. We did this jointly, and it was a very cooperative and very satisfactory process. And so the original design involved 196 piles, 1.5 meters diameter, 47.5 meters long. The podium, the outside area, the low-rise area, was on 750 smaller diameter piles, 0.9 meters, 30 meters long. And the raft itself under the tower was 3.7 meters thick. And here is the layout. There are basically 3 wings, so it's a very symmetrical layout of the foundation system. Now, Haida and ourselves did independent calculations by various methods to estimate the settlement. It turned out the geotechnical capacity of the foundation system was not a problem, that the controlling design element was the settlement and differential settlement. So Haida used a program called Repute and also a finite element program called Abacus, and got somewhere between 66 and 72 millimeters. We at Coffee used 2 methods. FLAC, the finite difference program, got 73 millimeters, and we used one of our in-house programs called PIGS, Pile Group Settlement, and got a very similar result. And then subsequently, we did a very simple calculation using an equivalent pier for the foundation and got an almost identical result. So that you can see that different methods by different designers got very similar results, somewhere between 65 and 75 millimeters for the estimated maximum settlement. And that was within the design specifications. Now, of course, it's essential in a project like this to do load testing to verify the design assumptions. And here there was a load test program which involved these tests: 3 static compression tests done on 1.5 meter diameter piles with toe levels 35, 45, and 55 meters long, just to see whether we could economize on the 47.5 meters that we had originally designed. We did 1 static compression test where we shaft grouted the piles to see whether that would increase the shaft friction. We did a cyclic compression test on a smaller pile to check the performance under cyclic loading. We did a static tension test for the smaller piles, and we also did a lateral load test. And the outcomes of this load test program were very favorable. That what we found was that the 1.5 meter piles were loaded to twice working load, the smaller piles to 3.5 times working load, and none of those piles appeared to be approaching failure, so that they had more than adequate capacity. The skin friction values were actually in excess of our design assumptions, so that was good. The shaft grouting was found to be effective but not necessary because we had adequate skin friction without the shaft grouting. The end bearing resistance wasn't fully mobilized because we couldn't get enough load into the piles to generate the full end bearing. The axial and lateral stiffness values were greater than predicted, and fortunately we found that the cyclic axial loading had little effect. So all of that was very positive. Now, during the construction, settlement readings were taken at the foundation base level, and these are the measured settlement contours when the building was at about 80% of its final height. And what happened here was that the good news is that the settlements were very symmetrical, that the maximum settlement was in the center and minimum settlements on the outside. And there were significant differential settlements between the center and the outside, maybe of the order of 10 to 12 millimeters, even though this raft was 3.7 meters thick, quite a thick raft, but because the building itself is about 55 meters in lateral extent, you still get bending of the foundation raft. Here are time settlement records. On the horizontal axis, the distance along one of the cross sections, and then the settlement here at various times. And the upper diagrams show the measured settlements at different times during construction. And this last one was at about 80% of the dead load, which was about 43 millimeter settlement. And this is our estimated, the design estimated final profile, which showed about 75 millimeters maximum. And we estimated on that basis that the final settlement would be of the order of 50 to 55 millimeters long term, which was, I guess, reasonably comfortable and certainly within design tolerances. So we were a little conservative in our assessment of settlement, but quite comfortably so. And just to give you some perspective, the structural designers estimated how much the building would shorten because of elastic shortening, also shrinkage and creep of the concrete. Now, what they found was, or what they estimated was, that the top of the building could shrink by as much as 300 millimeters. So our settlement of the order of 50 millimeters is actually significantly less than the structural shortening of the building. So here are three pictures of the building as it's being constructed early in 2006 when it's up around 10 or 15 floors, early 2007 when it's getting towards the top, and the grand opening where it was renamed the Burj Khalifa from the Burj Dubai, which happened very early in 2010. The next project I'll mention very briefly is also in Dubai, and this is the Dubai Creek Tower. It's a very new development in Dubai. It's about 8 or 10 kilometers inland from the Burj Khalifa. It's on what is really a big desert area. And the concept here is that there will be a whole series of high-rise towers with the centerpiece here, the Burj Creek Tower, being in excess of 1,000 meters. And it will be not a residential tower, but it will be an observation tower and a tourist attraction. And the people involved here were EMA, who was the client. The structural designer was Calatrava International. The foundation design was done by Oricon in South Africa. The foundation contractor was Salatanch Bashi. The testing of foundations was Fugro, and I was assisting Oricon with the foundation design. Now, the main challenges here again, we were now dealing with what will be one of the world's next tallest structures. Fast track construction was required. Again, we had carbonate soils and rocks, so there was capacity issues, but we also had extremely large lateral and vertical loads on this structure. The challenges were met here by intensive ground investigation. A lot of boreholes were done here, more than the Burj Khalifa, because this was a somewhat more extensive in area. High quality in situ laboratory testing. High-level design analyses were carried out by Oricon, the designers. There were a series of design workshops, and there was also a major load testing program. The foundation system itself consisted not of piles, but of barrettes. These are basically rectangular piles, 1.2 meters by, I think, either 2.8 or in some cases 6.2 meters wide. So very large rectangular piles. This is the foundation solution, that below the main tower, There were 145 barrettes, about 72 meters long. So you see, these are very large foundation elements. And on the outsides, anchoring the cables that you saw initially, under each one of these was 144 barrettes for the cable anchorages. And so these are the reinforcing cages for the barrettes, and this is the barrette installation. And this is an aerial picture of the foundation construction. There was a wall constructed around the tower area, some 10 meters deep, diaphragm wall, and within that there were the barrettes that were installed for the foundation system. And one of the interesting things was that with the load testing that was carried out on the barrettes here, that a new world record was actually set for the load to be applied to a single barrette, which is 360 meganewtons, which is nearly 36,000 tons on a single unit. So that is an enormous load. Now, unfortunately, that project has stalled. It has started, but it hasn't really been completed for various financial and other reasons. And I guess the COVID epidemic also contributed to that delay. But if and when it is completed, it will be, I believe, in excess of 1,300 meters. So it will really be quite a landmark tower. Now, those two projects have a number of positive elements. There was detailed ground investigation, including geophysics. There were advanced design methods used. There was a cooperative peer review process. There was detailed load testing. And certainly in the case of the Burj Khalifa, subsequent settlement monitoring, and that will be the case also with the Dubai Creek Tower. Now, let me conclude with a less favorable story. Now, this is the Millennium Tower in San Francisco. My involvement with this was very peripheral. I was not involved in the design. I was asked some questions by legal and media outlets about this design. So I know a little bit, but not a great deal. But this tower is 184 meters tall and 58 stories high. It's the tallest residential tower in San Francisco, and it is home to many very wealthy and influential people. It was founded on 945 reinforced concrete piles that were founded not on rock, as many of the tall buildings in San Francisco are, but was founded on a dense sand layer, and the piles were only about 24 meters long. And underneath the sand supporting those piles was a layer of, quite a thick layer of clay. Now, there were also, over the period of existence of this building, about 10 years, a lot of construction activities involving excavation and dewatering. Now, the maximum settlement of this building was found to be in excess of 450 millimeters, with a maximum differential settlement of 100 millimeters or more, and quite a significant tilt. And the residents noted that things kept falling off the table or things were rolling on the floor because of that differential settlement. There was a plan then by the original designers to install additional piles to increase the resistance on the low side of the building. Initially, that design called for 52 new piles, later modified to 18. But one of the problems was that when they started installing these piles, they also extended the pile cap and then started installing these board piles. They found that that caused an additional 25 millimeters of settlement. So installing the new piles actually made the problem worse. And so work was halted in September last year. It was resumed, I think, cautiously in December, but the tilt has continued to increase after the excavation for the foundation extension. So at the moment, I'm not quite sure where this building stands, but It's a very unfortunate situation, and I'm afraid that perhaps in hindsight, some of these problems could have been avoided. For example, the problems included the fact that the initial foundation design was what I call non-optimal, that it should have been recognized that for such a tall building, the underlying clay layers would be influential. There were nearby construction activities that caused ground disturbance. I don't think there was detailed monitoring of the settlements during construction, but there was after. And there was an inappropriate rectification scheme with attention devoted firstly to the low side before trying to correct the tilt. They perhaps should have started to correct the tilt on the side, the high side that had settled less before they tried to correct the stiffness on the low side. And so that scheme caused even more tilt. So just in conclusion, what I've tried to indicate is that there are three sets of analyses that we generally do in the approach that we adopt: an overall stability analysis, a serviceability analysis, analysis for structural design, and we also take account of cyclic loading effects to try and limit the loading on the piles so that we don't get cyclic degradation of skin friction. We are able, I think, these days to meet the challenges of tall building foundation design because we have modern methods that are being used for in situ testing, laboratory testing, analysis and design methods, and load testing. And in particular now with the Osterberg cell method being so widely used, we are able to get much better estimates of the performance of deep and very large capacity foundations. We, however, must always use simpler methods to check on advanced numerical analyses because some of these methods in some ways are black boxes to the users, and if you don't understand fully what the limitations of analyses are, you may come up with answers that are not appropriate. So you must always have some means of checking the results. We need to have cooperation between geotechnical and structural designers, and we need to be aware of the possible sources of problems in investigation, in design, and in construction. And finally, some of the precautionary measures that I've mentioned earlier should be taken into account to reduce the risks involved in the design and construction of high-rise building foundations. Thank you.
Thank you very much, Professor Poulos. It was a great talk. I learned a lot, particularly. I am sure the rest learned a lot too. Let's see if there are questions from the people here in the room Zoom, and also on the YouTube transmission. Let me check. Are there any questions from some of the professionals and students here in the Zoom room? Otherwise, I will start asking. I have a lot of questions. I have some questions. In the case of these tall buildings, particularly the ones that you referred to in this lecture, how the wind load compared to the earthquake or other type of loads, which was the controlling load in the design of the foundations? Maybe the winds. I am not familiar with the wind condition in Dubai, but I guess, I mean, any tall building should have problems with winds.
Yes.
So,
yes. Look, the wind loading is generally for tall buildings the primary factor for lateral loading. Certainly in Dubai, I mean, we had the design for earthquakes in Dubai because they've had I think a 6.2 a few years ago in Dubai. So no place on Earth is is not potentially affected by earthquakes. But certainly wind loading is a major issue, and wind tunnel tests are always undertaken to try and assess the wind loading. But almost invariably, in my experience, even in earthquake areas, the wind loading turns out to be a major issue. Where earthquakes are important, however, is when you're designing the piles for the kinematic effects, because there what you find is that if you have your piles or barrettes going down and you have a distinct contrast between stiffness of adjacent layers, that you can have bending moments due to the kinematic effects way down, so that almost invariably you need to take the reinforcement right down to the bottom of the piles to make sure that you have adequate strength against the kinematic effects. Okay?
I see. I see. Very nice. Thank you. There is something that has always intrigued me regarding because this is a tremendous building, right? And well, particularly here in Santiago, we have a very tall building which goes above 300 meters, if I remember well.
Yeah.
And but in those areas here in Santiago, in Chile, we have, particularly in the area of Santiago, central Santiago, let's call it that way, we have a very, very competitive soil. But in this case, we are seeing carbonatic soils and rocks.
Yes.
So it's not only that you have a challenge in soil, but it's also that you will have a humongous foundation, humongous in absolute terms. I mean, I understand it's only 5% of the building, but it's a massive foundation on a soil that is very easy to erode. So how do you deal with the protection of the foundation? That's an aspect in which you had some sort of decision, or it corresponds to another professional, in this case, to address how will the foundation live in such a challenging environment?
That's a good question, Felipe. Yes, look, it is a problem really for the pile designers and the concrete technologists, and the mix that is used for both the raft and the piles has to be such that it is durable for 100 years or more. And it's a particular problem perhaps in Dubai, because there the ground conditions are really not very favorable. The groundwater conditions, there's it's quite acidic, and so there have been durability problems with harbor structures in Dubai. But now, of course, with new concrete technology, the mixes and additives that are available are such that we can guard against that. And of course, the major problem occurs with durability where you have the really the groundwater level. At deeper elevations, it's not a problem. You have to have oxygen to generate durability problems. And most of the foundation system is actually below the water table, so that the conditions are not as severe as they would be, for example, with a port or harbor foundation system.
I see. I see. That's a topic in itself, the protection of the foundations, and not only the foundations, but also the environment surrounding the foundations, right?
Yes, absolutely right. And of course, that's why in the design team, you have to have concrete specialists mainly within the structural design and also within the pile design group, so that that issue can be properly addressed.
I see. So just a little bit more in depth on regarding that soil. Maybe it's when I think of carbonatic soils, rocks, I tend to think in erodible, let's say, sandstones, similar materials. So in addition to the high level of erosion that soil can have, with such a huge load, even it's well distributed with all the piling system, are there particle crashing that can induce, for instance, a secondary settlement?
Yeah, that's a good question, and I'm not sure that I could answer that. All I can tell you is that our initial concern was based on very weakly cemented carbonate deposits offshore. Now, these are probably more well-cemented deposits here, and I must admit that I was surprised at how little settlement we got. And this was part of the learning from the Emirates Towers, about 2 or 3 kilometers up the road, that we had predicted much greater settlements than were actually measured there. And so that was a learning that we took from that project onto the Burj Khalifa project, because we estimated more than, I think, 120 millimeters or so for the Emirates Towers, and they only settled about 40 or 50 millimeters. And so for whatever reason, the material is stiffer than we had originally thought. And so,
I see. I see.
But then, of course, again, we did the load tests, we did the laboratory tests to look at compressibility, and that demonstrated that indeed this material performs better than we had originally thought.
I see. I see. Yeah, it's the topic of collapsible soils is it's very nice. I mean, from the how to say it, from the behavior of the soil perspective.
Yes.
Understanding that the consequences are terrible.
Yes, but, from an academic viewpoint, it's a very interesting subject. From a practical viewpoint, it's terrible.
It's terrible, yes.
Because, and I mean, you know, we have cases in China and those sorts of places where they have collapsible soils and they try and avoid getting them wet, because if they get wet, they can collapse, you know, hundreds of millimeters. So, yeah, you have to be, I mean, this is where really having engineering geologists in your geotechnical team is important.
Absolutely.
They can identify those sorts of potential dangers.
Geology is key always.
Absolutely. Yes.
It's key. It's key.
Yes.
I really think, what is your opinion about that? Do you think in undergraduate, at the undergraduate level, maybe the geotechnical community should teach a little bit more of geology?
Yes, I firmly believe this. I mean, when the many decades ago when I did my undergraduate course, we did have a course in geology, and I think that was helpful. And that also included then applied geology, like engineering geology. In recent years, that seems to have been taken out of the courses because there are so many other aspects that are now included in undergraduate courses. But for geotechnical engineers, a knowledge of engineering geology is absolutely essential. And I think many of the problems that engineers have encountered is because of their lack of appreciation of engineering geology. And that's why it's so important that even if we as the geotechnical designers aren't that well versed in engineering geology, that we have somebody in our team that is. And yeah, it's critical. It's critical.
Absolutely. Oh wow! Out of the blue, a lot of questions came out in the broadcast. Let me double check some of them so I can read them to you.
Very good.
Okay, so we have one first question from Steve Adcock, sorry, and he asks, have you used near-surface geophysical method like GPR or seismic to evaluate older foundations without much design information and for a structural integrity of foundations, columns, and slabs?
Yeah, again, good question. Look, to be honest, I haven't used that directly, but I know it has been used, and it's something that is of increasing importance because I think one of the important areas now and in the future will be the reuse of foundations for old buildings, because there's a lot of either reconstruction on existing foundations or making an existing building taller or larger or heavier. And so that aspect is extremely important. And I know that what has been suggested by Stephen there is one of the methods that is being used, I think, fairly successfully to try and assess what your existing foundation is, because that's always the first step in evaluating whether or not the existing system is adequate, is to find out what it is. And then, of course, you've then got to quantify what its performance is in terms of capacity and stiffness.
Very nice. Well, and formally, geotechnical engineering will soon, let's say, well, it's already 100 years, but I'm thinking of that great conference in 1936. So probably yes, we are due with the recycling of foundations.
Absolutely.
Absolutely. Right. Yes. Absolutely.
Yes. Yes.
Okay. So there is another question from Ali Al-Batal. He really appreciates your talk. Thank you. He says it's a great presentation. And he says, you mentioned using conventional method for analysis to check. What is an example of conventional analysis method used for the Barrettes in the Dubai new structure?
Okay. Look, it's a very, very simple approach. And I think I mentioned it briefly when I talked about the Burj Khalifa, because what we do there is that you still have to have, of course, your geotechnical model with modulus and skin friction values. But what we do is we reduce the complex foundation system into an equivalent pier, okay? And you have an equal circumference of the pier, and you try and have an equal base area. And then there are simple elastic solutions for the settlement of the pier. And you can do that sort of calculation in 5 or 10 minutes. Whereas you mean finite element analysis takes you 3 or 4 days. It can, exactly, if it's really complex.
You mean? So, no, sir. Sorry.
And that's the sort of simplification. Some people like to use an equivalent raft analysis. I mean, that's been used for 50 or 60 years since Birham first introduced it, I think, in the International Conference in London in 1957. Where you sort of try and replace the foundation system by a raft at some depth below the ground, and then just use simple shallow foundation calculation. I've looked at these sorts of simple methods, and they're not bad. And I mean, it's important that when you do your calculations, you use that sort of method to let you know whether you're talking about settlements of 5 millimeters, 50, or 500. You can't get a really accurate answer, but you can get the what we call the ballpark figure.
Exactly.
And so that's where its real value comes in.
I see. When you mention that system is when you assume that basically if you look from afar, what you see is the system of piles and soil. They form some sort of a solid, right?
Exactly right.
Exactly. Yeah. There is nothing like analytical methods. The analytical will always be a must.
It's guidance. It's guidance. It may not and will not provide you with detailed analysis, but it will be guidance as to whether or not your answers from the computer are sensible.
It will always give you the first order result of
Exactly
your
right. First
exactly.
order. Yes.
It's a wonderful method always to have a sense of what you expect, and to address with proper criteria if your models are working properly.
Yes.
That's yeah, it's wonderful. Fabian Vite, he is an engineer, and he is sending you best regards from Ecuador.
Thank you.
Steve Adcock is also sending you a lot of regards. And Ali Al-Batal again, here he has a question, and he says, you mentioned that the load test in Burj Khalifa showed higher capacity that is way higher than the design values. Did you optimize the length of piles based on the load test?
To be honest, we didn't. I guess the design there was really controlled by settlements, and subsequently we did go back and re-examine the settlements, and what we found was that using the load test data, had we used that data, we would have estimated settlements of about 50 to 55 millimeters. We got 75, but I mean, it was still fine. I mean, if you're going to be inaccurate, you be inaccurate on the conservative side. And so
yes, definitely,
I think
especially for such a tall building.
That was what was decided. Yeah.
Okay, so the next question is replied in the question here, and a lot of regards also from Brazil. Which I think you have been to Brazil.
I have many good friends in Brazil.
Very nice, very nice. I have one last question?
Of course.
Maybe 1.5. By any chance, did you do any plate load test, maybe watering the soil at the same time, just to understand how the soil would behave with a very large load under, let's say, the worst condition, maybe?
The answer is no, we didn't do any plate load tests. And what happened, I guess the reason that it wasn't a major issue in the projects I've talked about is that as it turned out, although the foundation was designed as a piled raft, under serviceability conditions, the piles were taking more than 90% of the load, so that the raft itself wasn't that influential. If we have other projects which perhaps are not so tall, then the raft can be designed to take a significantly larger proportion of the load, 40 or 50%. This has been the case, in fact, in Frankfurt, where some of the foundations there designed have assumed something like 50% of the load taken by the raft, 50 by the piles. There, of course, you have a greater level of concern about the compressibility of the raft and the soil under the raft itself. But when you've got the majority of load that's been carried by the piles, then your concern about the stiffness of the soil below the raft is less important.
Very nice, very nice. Thank you. The last question, yes. Because I think we are done here with the questions. Because it's also we have taken a lot of your time. So, what is the do you know the numbers regarding how much of the geotechnical characterization represented with respect to the total value of the project?
Oh, look, that's a really good question. And I don't really know. I think because, let's say, the Burj Khalifa was such an expensive project that the ground investigation would have been much less than 1% of the cost of the building.
Much less than 1%.
That's the investigation, not the
yes, exactly, the investigation. Wow, I am surprised.
Yeah, I would say that, I mean, there was quite a lot of geophysics, and I'm only guessing, but it's just that the building itself, I can't remember what it was. It was something like $400 million. So, I mean, 1% of that is still,
okay.
it's $4
still
million.
A lot of money.
And that's quite an extensive ground investigation. So
I see.
it would be, maybe it would have been around $2 or $3 million or thereabouts.
Oh, I see. I see.
That's just a guess. Look, don't hold me to that.
Okay. I thought it might be, I don't know. Today in the morning, I was taking an exam to our students. Yes. And we were discussing the ground characterization for a house. Yes. And I was saying, okay, for a house, maybe 0.5% of the price of the house. And my guess for this building was, let's say, 2% or 3%.
Ideally, yes.
But based on what you mentioned, right, it's a tremendous project, very expensive. So yes. the ground characterization is even less. You're right.
Yes. Look, I think we have to separate percentages because the building is so extraordinary yes. that its cost is so high that we need to look in terms of absolute costs. And this is a very extensive and expensive ground investigation. But that's the reality.
Very nice. Very nice. All right. I think. Okay. Here we have one little question. Just sorry. Jose Carlos Coya, he's asking if this structure is monitored from a geotechnical perspective.
Good question. Look, I don't know whether they're continuing to monitor the foundation performance. I don't think so. I haven't got any recent measurements of the settlement. I do know that they're monitoring the structural performance because they're still quite interested in the dynamic response under wind loading. So Samsung, who were the major contractor, do have records of the structural response of the building to winds. But I don't think because the settlements were relatively insignificant, they haven't continued to monitor those.
I see. All right. Professor Poulos, we're so happy for all the opportunity, the lecture and the discussion. We really appreciate your time. We really appreciate you took the time also to share your knowledge with us. And this is the end of this great talk. Thank you very much to everyone who came here to University of Chile. Today I had to take the lead of the presentation. Here Karina does a great work, and we missed her a lot in the preparation of this talk. So thank you very much. We can stop the YouTube broadcast, and I don't know how to stop this. But
I'll stop sharing. And again, thank you, muchas gracias, everybody, for taking the time to listen. Thank you.
All right.